David Spieth here with one more flipped classroom math video lesson. 3 tips before we start. First, you can adjust the playback speed faster or slower as you desire. Second, you can pause the video at any point to catch up with notes or write down some questions. Third, you can turn on the captions and read my words on the screen. Today's topic, limits review. So we've spent the last couple, 2.5, 3 weeks working on limits. So this video is going to be a quick walkthrough for all the things we did in this particular chapter. So let's get started. First off, notation. The limit as x approaches c of f of x equals L. So this is our way we talk about limits mathematically with our notation. X is your x in your function. C is some constant that you're trying to approach with your function. And you're trying to see if that function actually has a limit. Now before we go into an actual function here and how that looks, the idea of a limit is like this. If there's a wall over there and I walk halfway to the wall, and then each time I walk another halfway to that wall, technically I never get there, right? I'm always walking halfway there. Never going to get there. I'm always going to make that distance between me and the wall half as big as it was last time. But the limit is the wall. I'm never going to get there quite, but I can't get beyond that for sure. So the limit in that little example is the wall. Okay, so let's take a look at a function. Here's a function. We're taking x to 0, and we want to find out what the limit is. Now take a look. It's x over root of x plus 1 minus 1. Now, we can't plug 0 in here, because if I plug 0 in for x, it's going to be root 1, which is just 1, minus 1. I have a division by 0 problem on the bottom of my fraction. I can't plug the 0 in and evaluate that limit. So one of the techniques that we used was a table. And we use this on a graphing calculator or in Desmos or any number of electronic tools that let you analyze functions. So what I've put here is a little table where it shows the input x and the output f of x. And I'm just approaching 0 from the negative side. I'm getting closer and closer to 0. And I'm approaching 0 from the positive side, getting closer and closer to 0. So these values are converging on 0. And then look at our f of x. 1.995, 1.99995. So we're getting really close to 2. And check this out. This one is also getting really close to 2. So even though we can't plug 0 in for x and directly analyze our limit, the table shows us that this limit is 2. Okay, so there are some cases with functions where when you approach a particular constant, there is no limit. So these are limits that fail to exist. Let's look at just one of those. Here's the function, 1 over x, the limit as x approaches 0. So what's the limit of that? So let's take a look here. As I approach 0 from the positive side, I put 0.1 in for x, f of x is 10. I put 0.01 in for x, f of x is 100. 0.001, 1,000. So when we approach from the positive side, we're just growing big. Another way we say this is f of x is increasing without bound. It's just getting bigger and bigger and bigger. So we're not approaching a number as we approach 0 from the positive side. Let's take a look at from the negative side. Same problem. We're just approaching a more and more negative number, a smaller, smaller, smaller number. Because as I approach 0 from 0.1, negative 0.1, negative 0.01, negative 0.001, I'm going negative 10, negative 100, negative 1,000. So I'm decreasing without bound. So there's 2 reasons this limit fails to exist. One is that depending on which side I approach 0 from, I'm either increasing without bound or decreasing without bound, so that's a problem. The other thing is I'm going the other direction, okay? So this function is getting increasingly negative, or this range of input values are making the function get increasingly negative, whereas when we use this range, it's going increasingly positive. So 2 big reasons for why there's no limit as x approaches 0 of 1 over x. So we could write no limit. Okay, one of the primary tricks that we use to evaluate limits is called dividing out. So I'm going to show you a straightforward example where we use that technique. Check out this function. I have the limit of x squared plus 2x minus 24 over x plus 6 as x approaches negative 6. So we can't evaluate this limit by just plugging in negative 6 for x because we have a division by 0 problem. So this expression goes undefined. So we have to use this dividing out technique. And this is where this course stands on your prior knowledge of algebra. So you've got to look at this top expression here and see that that factors into x plus 6 times x minus 4. And then we have x plus 6 on the bottom. So all I did is I just factored this top expression into two binomials, and now I can cancel, which is called dividing out in this case. So I get rid of my x plus 6, I get rid of the annoying thing on the bottom that goes to 0 that stops me from evaluating the limit, and now I can write the limit as x approaches negative 6 of this new expression x minus 4. Now I can just plug negative 6 in for x. I don't get a divide by 0 problem, and so I have negative 6 minus 4, that's going to be negative 10. So that's my limit for this function. One more technique is called rationalizing the numerator, and it helps us deal with the divide by 0 problem. The limit of this expression as x approaches, or as y approaches 0. We can't do a direct substitution and plug in 0 because we have our divide by 0 problem. So what we do is we multiply the expression by 1, but it's a weird version of 1. Watch this. Okay? This might look really complicated, but it's just 1. Same thing on the top as the bottom of a fraction. That's just 1. But what I did is I multiplied it by this thing plus this thing. See, there's the plus. This is the minus. And what I'm doing is I'm exploiting the difference of squares expansion pattern. So when I multiply across the tops, I'm going to have this, the result of that expansion pattern is this thing squared minus that thing squared. And what the squaring does is it just removes the square roots from here. So what we get is 5 plus y minus 5. Okay, so that's what happens to the top. This is super simple, and check this out. The 5's are going to go away, and I'm just going to have y on the top. Now let's take a look at what happens on the bottom. I'm actually not going to distribute this y onto these two terms, because what happens here is I'm going to be able to cancel. So I'm just going to carry this over like so. And then carry it over again. And I can cancel my y's out, like that. So now what I have is the limit as y approaches 0 of 1 over 5 plus y plus root 5, just like that. And now I can plug 0 in for y, and I don't get a divide by 0 problem. So now I'm just going to end up with 1 over root 5 plus root 5, which is 1 over 2 root 5. So that's the limit of this function as y approaches 0, 1 over 2 root 5. Next, we looked at one-sided limits. So what this basically is we're approaching our constant from one side only. So this is approaching negative 1 from the positive direction. So we're coming in from the right. So this is the limit of that expression as x approaches negative 1 from the positive side. So let's evaluate this limit. So I can't plug in negative 1. I'm going to get a divide by 0. So this one is going to be solved by factoring the top. This is going to be x plus 1 times x plus 1 on the top. And again, over x plus 1. Now I could write x plus 1 squared, but I don't want to do that because then I can cancel those. And I can get limit as x approaches negative 1 from the plus side of x plus 1. And now I can just put negative 1 in for that, and this is going to go to 0, so that limit is 0. Okay, next we looked at using limits to discuss the slope of a tangent line and actually to create a derivative function that allows us to calculate the slope of a tangent line at any point. So I'm going to go ahead and do that for you now. First off, we came up with this definition for the slope of a tangent line. The limit as h approaches 0 of f of x plus h minus f of x all over h. And that relates to the graph. Here's our increasing function. It's not linear, so the rate is constantly changing. What we want is to find the slope of this tangent line. And what we do is we take a look at 2 points. This is the x-coordinate here, and we increase it by h. So this is x plus h. And then the y-coordinate of this point is just f of x, and this is just f of x plus h. So what we do is we make h smaller and smaller and smaller, so the secant line connecting these 2 points gets closer and closer to the actual slope of the tangent line. So this is where the f of x plus h and f of x come from in this formula. What we're doing is we're just doing the change in y over the change in x. That's all this is. The change in y is f of x plus h minus f of x. That's this distance. And the change in x is just h, that distance there. So to find the slope of the tangent line, we take the limit of that expression as h goes to 0. Okay? So let's take a look at that for the basic x squared function. Okay? So what we're going to do is use this formula to evaluate x squared. So this is the step that people struggle with the most. I call it the plug-in step. Everywhere you see x in the function, you want to plug in x plus h for this first part. So this would be x plus h squared minus x squared. So here is f of x plus h, boom, and here is f of x, which is just our x squared function. This is over h. Now we have our divide by 0 problem. We can't plug in 0 for h because we get divide by 0. So now we have to manipulate this function to be able to cancel out the h's so we can directly figure it all out. So watch this. X plus h squared is going to be x squared plus 2xh plus h squared. And then I have my minus x squared there, all over h. Now I got some interesting things going on. X squared minus x squared. Those just go away. And that's going to leave me with 2xh plus h squared over h. Now I have an h term, an h in both those terms, so I can cancel. It's going to cancel out that h, and it's going to lose the squared on that one. So this is going to end up being 2x plus h. We got rid of our divide by 0 problem. So now we can take the limit as x approaches 0. Let's just put that over here. I said x. It's as h approaches 0, because now we're dealing with h's, of 2x plus h. Now as h goes to 0, this is just going to give us 2x. So that's the derivative function that we can now use to analyze and find the slope of a tangent line at any point. So for example, we know that on this point, on this function, there is a point 2, 4, right? If x is 2, plug it into our function right there, and f of x would be 4. So what's the slope of the tangent line at the point 2, 4? All you do is you take the 2, which is the x-coordinate, plug it in to your derivative function, and you're going to get 4. So the slope of the tangent line at the point 2, 4 is 4, because that's our function that tells us how to do that. We also looked at limits as x approaches infinity, okay? And that can happen from the positive or the negative side. So here's how that looks in the notation. The limit as x approaches negative infinity of this function. So before we get into it, let's rearrange this just a little bit to make it easier to work on. So I'm going to distribute the negative on both these terms. I get minus x squared minus 3 on the top. Now I'm going to go ahead and expand that. That's going to give me x squared minus 4x plus 4 on the bottom. Now I can start evaluating the limit. Action. So our technique for that is to pick the highest degree term on the bottom of the fraction and divide the whole thing through by that, like so. I'm going to divide this by x squared over x squared. I'm just dividing by 1, so I can do that all day long. I'm not changing my function. So this is where it gets really fractiony, but buckle your seatbelt, it actually resolves pretty easily. So let's carry this down to a new line. Now what I'm going to do is I'm just going to divide all the terms by x squared. So I'm going to get minus x squared for that top over x squared, minus 3 over x squared. This is all over x squared divided by x squared, minus 4x over x squared plus 4 over x squared. Now I can look at what happens to these terms when I run x to negative infinity. what's going to happen to x squared over x squared? That's just going to be 1. This is just, or negative 1. Take a look at that. That resolves to negative 1. What's going to happen to this term as x squared goes to negative infinity? The bottom of this fraction is going to get huge, which means the overall fraction is going to go to 0. So this is going to be negative 1 minus 0 over, now take a look at this. X squared over x squared, that's just 1. 4x over x squared. When x goes to negative infinity, the bottom is going to grow really fast compared to the top. So this is going to go to 0. And what's going to happen to this one? Same thing as this one. It's also going to go to 0. So what do we get here? Negative 1 on the top, 1 on the bottom. So we're going to get negative 1. That's our limit. The last lesson we did in this unit dealt with limits of sequences. So a sequence is just a set of numbers that just increases or decreases according to some rule. So this sequence that I'm going to use here, a sub n is like the nth term of the sequence. It's calculated by plugging in whatever term number that is into this function, and it spits out the sequence. So a sub 1 is 1. If you plug 2 in for the second term, a sub 2, you're going to get out 3/5. A sub 3 is 2/5, and so on. This thing can march on to infinity. In fact, what we're going to do is we're going to take the limit when n goes to infinity. What's that infinite sequence going to be approaching, that last term? You can't have a last term on infinity, but it's getting towards a certain number. So what's the limit of n plus 1 over n squared plus 1 as n approaches infinity? So we're going to use that same trick we used in the last board. We're going to divide through by n squared over n squared. That's the highest degree term in the denominator. Now I'm going to write that big, ugly looking fraction. I have n over n squared plus 1 over n squared. That's the top. My bottom is going to be n squared over n squared plus 1 over n squared. So now I can look at each of these fractions and figure out what's going to happen. So n over n squared. The bottom is going to grow much, much faster than the top. So as we approach infinity, this one's going to go to 0. Okay, so this is going to be 0 plus. Now this one's going to work in the same way. It's going to get to 0 faster because now we don't have this n on the top that's also increasing. We just have n squared on the bottom. So 1 over n squared as n goes to infinity gives us another 0. So you can kind of already see where we're at. We have 0 on the top of our fraction. There's no way this fraction can end up being anything other than 0 as long as we don't get undefined on the bottom. So let's take a look at that. N squared over n squared, doesn't matter how big n is. This is 1. And 1 over n squared, we know from up here, that's going to be 0. So this is 0 over 1. So that's not undefined, that's just 0. Now that you've watched the video, take a minute to jot down some notes, some questions, or a quick summary of the lesson. You can also re-watch portions of the video that were a little bit challenging the first time. If you enjoyed the video, please click like. And if you'd like to help me grow my YouTube channel, please click subscribe.